I think my real interest, if I traced it back, was curiosity about the physical world, which is what physics is.
One might imagine, at least, that one's talking about nature when one's talking about the character of physical laws. But I don't want to talk about nature, but rather how we stand relative to nature now. I want to tell you what we think we know, and what there is to guess, and how one goes about guessing.
This is the piece of the equation which describes how the Higgs field acquires its value.
Research infrastructure like CERN and Sesame to foster physics and to better understand the world around us. So check our public lecture library, where we have more than 50 YouTube recordings that witness why physics matters. So last November, we celebrated together 70 years of existence of CERN, so with Luciano Mossa. Today, we're going to celebrate 40 years at CERN, so for Maurizio Vretenar, that you will hear later, but also tomorrow, so on February 28th, so we will celebrate the 101 years old of Erwin Schopper, who is the former director and the founding father of Sesame. So it's really like a nice moment as well to celebrate all of that. And I would like to quote then Erwin Schopper, as so Maurizio was just mentioning, speaking about what makes life really exciting and why you can live longer. This is the secret. The secret of this long life is not only the gene, but this is also the curiosity. And this curiosity, this is what we tried as well with this physics matter to embody. So good health, it also resonates with particle accelerator. So you can navigate also earlier in our colloquial library, where you will find at least at the end of the last year, 3 special presentations that were picturing particle accelerator and healthcare. So today, the panelist is composed of Andrea Lossi, who is the Sesame scientific director. We have also with us Alan Hurd, from Los Alamos, like myself, former chair of the Forum of International Physics, and Forum of International Physics member at large. With us, we also have Sirius Walter. So we will then be able to follow with question and answer after this presentation, which will last about 40 minutes. And today, we have the honor to welcome Dr. Maurizio Vretenar, who will highlight those different access of particle accelerator spin-off activities. So to describe his long career, he's a senior accelerator physicist and project leader at CERN in Geneva, in Switzerland. He earned his PhD in physics at the University of Trieste in Italy, and he joined CERN then 40 years ago, in 88, to participate in project related to the design, the construction, and the operation of LINAC particle accelerator, those LINAC. So after being responsible for accelerating system of the CERN Hadron Collider, the Hadron LINAC, so he has been also project leader for the construction of the LINAC 4. So this is this new LINAC injector for the CERN Accelerator Complex, which has been commissioned in 2017. Since 2013, he is also coordinator of a series of EU-supported projects to promote innovation for particle accelerator, like, for instance, the ECAR2, the ARIAS, and then also the ongoing IFAS, which is Innovation for Fostering Accelerator Science and Technology. And I recall that in February 23, we had as well one presentation of the challenge-based innovation, which is part of this large program, IFAST, by Nicolas Delarue. So more recently, so he has been also increasingly active in the design of compact accelerator for social application, with a particular focus, so with the medical field. So where in 2019, he became to lead the next ion medical machine study, the NIMS, which is an international collaboration led by CERN to advance the cancer therapy with the compact ion accelerator. So it will be a pleasure to have your question after his presentation. You have a Q&A session that you can already prepare your question in, and we can also give you the microphone if you want to ask the question live. So we are looking forward to hear more, and so then the floor or the screen is yours, Maurizio.
Okay, thank you, Christine, for your nice introduction. I will start sharing my slides. Yes, and wishing good morning, good afternoon, or good evening to all of you. Now let's go to full screen. Yes, okay. Can you see the slides in full screen?
Now, yes.
Yes, okay, great. So we were talking about curiosity, and it will be a pleasure to bring you with me in a travel through the fascinating world of particle accelerators. I hope that I will be able to present you what is the potential of accelerators, what accelerator can do, what is their potential for society, what they can do now, and what they will be able to do in the future. So, but anyhow, let's start with our idea of accelerators. So when we think of accelerator, we only think to the very large objects. We think to the Large Hadron Collider, we think to machines that are huge, and they are huge, because accelerators are the largest machines ever built by humankind. And it's not me who says that, it's the Guinness Book of Records that has declared that the Large Hadron Collider at CERN is the largest and most complex machine ever built. Actually, the LHC at CERN is 27 kilometers, but 11 kilometers of injectors and beamlines, so total 44 kilometers, is millions of meters of cables going underground. It's 100,000 square meters of laboratories. So really, these are huge machines. And even larger will be the next generation. There are now studies at CERN to build a machine, the Future Circular Collider, of 91 kilometers length. So these are huge machines. You can see here the tunnel of the Large Hadron Collider. This is an artist's view of how could look like the Future Circular Collider. You see, you don't even see that the tunnel is circular. It looks really straight at 90 kilometers. These accelerators are equipped with huge detectors, like this one, the CMS detector. So, huge machines. And why are they so big? So, as the little duck says in this cartoon, the point is that the smaller the thing you want to observe, the bigger the instrument you need to observe it. Why? And this is something that I hope to be able to show to you. But first of all, let's say that the big machines are only the visible part of the iceberg. Those are the more visible, the more known accelerators. But most of accelerators are used in everyday life. What people usually don't know is that there are 17,000 linear accelerators working in hospitals all around the world for treating cancer. Those are the famous radiotherapy linacs. There are 12,000 ion accelerators that are used for implantation in semiconductors. There are almost 2,000 cyclotrons around the world for production of isotopes, and there are many machines used for industrial applications. So scientific accelerators are actually only, in terms of numbers, a minority. Research machines are only about 6% of the nearly 40,000 particle accelerators in the world. And out of these 40,000, only less than 1% are those used for particle physics. The other machines are a bit everywhere, in medicine and in industry. And here, when I speak of accelerators, I speak only of accelerators of voltage above 100 kilovolts, so giving already a certain amount of energy. Because, for example, we don't mention the old cathode tubes that also were very nice electron accelerators. So this was, maybe it was the first and most important use of beam acceleration was for television. You see, so accelerators are everywhere. But why are so popular? What do they all have in common? From the LHC to the small cathode tube of the old TVs. So an accelerator is an instrument. Is an instrument that has the goal of concentrating energy at the subatomic scale. So basically, we can think the accelerator as a black box that gets some energy from the electricity grids and then concentrates this energy into a small particle beam that has different applications. In this process, unfortunately, a large fraction of the energy is lost. So accelerators produce waste heat, and we will see, how much and how we can deal with it. But the goal is to concentrate energy. But how much is this energy? So to give an idea, I usually propose a small contest. Let's compare the energy of 4 objects. We can take a proton out of the Large Hadron Collider, 7 TeV energy. It's a huge number. We can compare it with the energy of a bunch of protons out of the LHC. A bunch is already 10 to the power 11 protons. But I propose to compare these particles with a yogurt. For example, a yogurt that you could have had this morning for breakfast. And then let's compare it with the energy of a high-speed train traveling at 300 kilometers per hour. What is the energy of the LHC proton? If we convert the 7 TeV into joule, our standard unit, and I remind you that the joule is very, very small. The joule is only 1 watt per second. So basically, here in Europe, I can buy 10 megajoules with only €1. So it's really nothing. And the energy of the proton is 10 to the minus 6 joule. So 10 to the minus 6 times nothing. It's really very, very small. Even the energy in the complete LHC bunch, it's 10 to the power of 5 joules. It's already something, but it is still smaller than the chemical energy contained in your yogurt, which you can easily calculate because you can read on your yogurt that usually it has 120 calories. You can convert the calories into joules, and you get 10 to the power of 5, which is still, much, much lower than the train. The train is 10 to the power of 9 joules. So, no surprise, in our energy contest, is the train that is the winner. Second comes the yogurt, third the bunch, and last our LHC proton. But let's look at the energy density. How much is the energy density in these 4 objects? Then, okay, the train is 10 to the 5 joules per cubic meter, which is much, much smaller than the yogurt, which is pretty good. 10 to the power of 9 joules per cubic meter. But still, a bunch of particles out of the LHC reaches 10 to the power of 12. So, okay, they beat the yogurt. But if we calculate the energy density for the proton, taking the classic radius of the proton, we come to the frightening number of 10 to the power of 38 joules per cubic meter. So the point is that the energy contained in our particle beam is relatively small, but the energy density is huge. And we can reach the highest energy densities in nature thanks to our particle accelerators. And you see that in terms of physical objects, the yogurt is 10 to the power of 9, that is comparable to our best ways of storing energy. That is still, gasoline, it's something of the order of 10 to the power of 10 joule per cubic meters. Still, an order of magnitude better than batteries. And this is why, electric cars have such a problem to penetrate in the market. Okay, but this is another problem, another story. So I hope that I have convinced you that particle accelerators are instruments that can concentrate huge amounts of energy at atomic and subatomic scale. And they are unique tools. They are the only instruments that can do that. Now, we have this energy. What can we do with this energy? Where does the energy go? What is it? There are actually, so if we send our beam of particles against a material, that can be a target, an object, can be other particles, our particles interact with the atoms, interact with the nuclei, and have different effects. They can ionize, and this is an effect on the chemical bound, so they can break molecules, they can generate free radicals, and they act at a chemical level. They can act at a thermal level, because they can transfer energy to the nucleus, and then they can excite electrons that then come back producing X-rays, so they can produce secondary beams, and they can, if they interact with the nucleus, break or modify the nucleus. Not only, but if they can, the energy density is so high that when you have collisions between high energy particles, you can generate new particles. And this is very important because it's the reason why accelerators were born. Actually, the big excitement about accelerators came in the first years of last century when Rutherford asked for more accelerators to transform the matter. Actually, accelerators are dream machines because particle accelerators were invented to, actually every technology starts from a dream. And the dream of accelerators was that of transforming matter. Thanks to nuclear physics, thanks to the effect of high energy density collisions of particles with the nuclei of the atoms, you can change the atoms and you can transform the matter. And this was the dream of the ancient alchemists. And if this was not enough, then in recent years, another dream came true thanks to particle accelerators. There was the dream of creating matter. Actually, not creating matter, but transforming energy into matter. Transforming the energy into the collisions to create new matters and to create, for example, Higgs boson or whatever type of fancy particle you can imagine. So two dreams, but also for us today, if you want to explore the societal applications of accelerators, it's important to speak about a third dream. That is the dream of bloodless medicine. Particle accelerators, particles can penetrate into the tissues, into the body, and can interact with the body, can create imaging of the inner parts of the body, and can cure the body without pouring blood, thanks to the fact that the energy is deposited, as we will see, by some type of particles, not on the surface, but at a certain depth. And this is also an ancient dream of humanity, being able of observing and treating the body without blood. So, wonderful dream machines. In principle, we can imagine that we can do everything with accelerators, but there is a limitation that we have to take into account, which is energy efficiency. So, we concentrate energy, and to concentrate energy, we have to go through different energy transformations. And every energy transformation has an efficiency that is, by definition, less than 1. So we always dissipate some energy. Basically, we go from the electrical grid. So we have somewhere we have a plug where we have plugged our accelerator. We take the energy, and then you see for normal conducting accelerators, so these are examples that you have in this slide that, let me take my pointer. Yes, this is an example for a linear accelerator where where one takes the electricity from the grid, converts it to high voltage, then from high voltage to high frequency, then from high frequency to electric field, and then the particles get the energy from the electric field. At every energy conversion, you lose some energy, and some of these conversions have a particularly low efficiency for basic fundamental reasons, like the conversion from high voltage to radio frequency. It's the same if you want to use superconducting accelerators. Then you would say, okay, well, I don't have losses, so it will be much better. Well, not, because then you are dependent on the cryogenic efficiency, and this is really thermodynamics. Carnot efficiency, something that limits the efficiency of your accelerator. That is, I remind you, a system to transform energy. And the result is that at the end, a lot of energy will go into waste heat. So accelerators are wonderful instruments to concentrate energy, but to go from low quality energy to high quality energy in the particle beam, you have to invest a lot of energy. This is an example in this slide of the energy flow in a large accelerator. This was done by my colleagues of the PSI laboratory in Switzerland. They have a big cyclotron, and they've calculated that at the end, only 10% of the energy that they take from the public grid goes to the beam. The rest, 90%, where does it go? To heat. It is dissipated, in their case, to the air or to the river that flows near to the laboratory. So accelerators, so there is a lot of work in the accelerator community to improve the energy efficiency of accelerators. It's an engineering problem that can be partly solved, but at a certain moment you hit fundamental reasons why the efficiency of accelerators remains relatively low. So in this case of PSI, we have seen 13% efficiency. Accelerators for particle physics have even lower efficiencies, less than 1%, because the goal is really to create new particles with such a high concentration of energy that the dissipation is huge. And only systems that are specifically designed for high efficiency can reach a maximum of about 50%, but only in small scale and for special application. So basically, concentrating energy into a beam creates a drastic local reduction in entropy. It's all about entropy and thermodynamics. So accelerators are very good, but are, let's say, expensive objects in terms of construction, but also in terms of energy management. So this is why we will now speak about use of accelerators in industry. They are very good for very specific applications, but they cannot be usually they're not used for large processes where the limitation is given by the energy and the cost required in the process. So they're very good in do very special things at very, very small scale. But okay, now it's the moment, okay, 20 minutes to go to the second part of my talk. That is to go to see where do we find accelerators outside of scientific laboratories. So there is a big landscape of accelerators that we want to explore. And this is how artificial intelligence sees a landscape of accelerators. So we ask ChatGPT, what is a landscape of particle accelerators? And this is the answer. But what I said is that accelerators are very good in concentrating energy, but they don't have much energy content in the beam. So an ideal application actually is medicine, where, like any drug, the point is to limit the effect to the body, and the fact that you don't have too much energy into the particle beam helps really not to kill the patient. So, and there is really a large number of applications that we find for accelerators in the medical field. You see here this small cartoon that shows the different ways a particle beam can interact with the patient. So you can send on the patient directly your beam, and this is something that is usually used to treat cancer. You can treat cancer with proton beams, with ion beams, and together this is called hadron therapy. You can use electrons directly to treat directly on tumors, on tissues around tumors. You can treat with electrons at high energy, but as I said before, the most widely used application is by using secondary beams, X-rays. So electron accelerators can produce beams of X-rays, and this is the conventional radiation therapy. Okay, this slide is quite old. Now the number is more 17,000 of machines of this type. You can use also other secondary beams, neutrons, for example, or there is another interesting way of using the accelerators, that is not to send the radiation directly to the patient, but to generate the radiation in the laboratory and then ship it to the hospital, produce radioisotopes that are transported to the hospital and then are injected into the patient, radioactive compounds, and this can be used for imaging. 1,500 accelerators are used to produce isotope for positron emission tomography, or they can be used directly for therapy. So a large number of applications. And really the most widely used, the pillar of cancer therapy, is the radiotherapy LINAC. 50% of all cancer patients nowadays require treatment with this type of machines. You see, machines are made of, can rotate around the patient. The accelerator is a small linear accelerator of about 1 meter length, and then the beam is sent on a tungsten target where the X-rays are produced. What is interesting is that this type of, most of the radiotherapy accelerator nowadays use a small linear accelerating structure that you see here. It is called the side cutter structure. This was actually invented in Los Alamos in the 60s for their meson physics facility. And it is very interesting that it took many years until a new development that was done for science, in scientific field, moved to medicine and became really the workhorse of medical accelerators, thanks to its properties of high efficiencies. We say that efficiency is important, and in fact it's important to invent accelerators that have a high efficiency in terms of power, I mean dissipation of power from the grid, and then in terms of stability. So what is important for the accelerator for medicine is that it must be very stable, must operate in difficult environments with little technical support, and is really an ideal structure. Turned out something that was invented for the Los Alamos Meson facility turned out to be really the workhorse of modern medical accelerators. But they are not only X-rays. X-rays are very useful, but they are very light. Photons have no mass. And there are many advantages of using particles that have mass, actually. So going from X-rays to protons or helium ions, helium nuclei, or carbon nuclei. So what is the difference? The difference is in the dose deposited inside the tissues, as you can see from this graph. So X-rays deposit most of their energy at about 10, 20 centimeters inside the body. So these curves here are for energy deposition in water, but being that our tissues are mainly made of water, this is about distribution inside the body. So X-rays are very good to treat tumors that are close to the surface. If you want to treat tumors, deep-seated tumors, then there are many advantages in using particles that have what is called a Bragg peak, meaning that their energy is deposited at a well-defined depth that you can change by varying the energy of your particle beam. So this peak can move, and you see here, this peak is different for protons, helium, or carbon. The higher the mass, the narrower becomes the peak, but you start to have some fragmentation tail at high energy. So in general, it is, so heavier ions are better in terms of thickness of the Bragg peak, in terms of action on the cells, so their damage to the cell is different, is more important, but they also lose more energy. the energy deposition in the body is higher, the higher the mass. But this unfortunately means that if you lose more energy, you need more energy to reach a deep tumor. And more energy means a larger accelerator. So the larger the energy, the larger your accelerator, and the larger accelerator, the higher the cost. And you can see here a small comparison of Linux for X-rays are machines that are there that are relatively not inexpensive and occupy only a few meters. Cyclotrons for proton therapy are large and 10 times more expensive than X-ray Linux. But if you want carbon ions, you have to build big synchrotrons that become very expensive. And this is really an expensive type of treatment. Expensive type of treatment that is growing more and more in the last years. So this is a curve that shows how many particle therapy facilities were installed over the years. And you see that now that we are going through a kind of a linear growth of proton therapy facility. So there is more demand for proton therapy, and they really are, particle beams are the nuclear scalpel of the 21st century. So bloodless therapy, they can treat a tumor that is inside the body very precisely. Their limitation is exactly in the precision. So being a very precise tool, you need a very precise environment to be sure that you deposit the dose exactly where you need it. Otherwise, it is ineffective. And so this is why it takes a long time now. It is taking a long time for this type of treatments to enter into the everyday clinical practice in every hospital, because you need a lot of, you need improved diagnostics, you need improved beam delivery, you need excellent softwares to be sure that you control the deposition of your beam. Nevertheless, I mean, this is now more and more recommended in the medical field, in particular for tumors that are close to critical organs and for pediatrics, because for pediatrics, not only you have a very difficult environment with the organs very close one to the other, but also you don't have if you reduce the radiation, you have less risk of recurrency of developing the cancer many years later. So, but the diffusion, another problem of something that also that limits the diffusion of particle therapy of cancer is the fact that these machines are mainly meant to improve quality of life. So actually the effect on the mortality is not so high, treating with the normal X-rays or treating with particles. But where we start to see a big difference is in the quality of life after treatment because of sparing the organs that are next to the tumor. So this is why, I mean, now particle therapy is growing, and there are many ideas around on how to improve, how to further improve the penetration of particle therapy. There are new ideas, there are new accelerators in construction. What is interesting nowadays is that carbon ion therapy is becoming commercial. There are now 2 companies that are building commercial ion therapy systems. One is building, Hitachi is building for the Mayo Clinic in Florida, the first US carbon ion therapy facility, and IBA is building a superconducting cyclotron in Europe at Cyclades in Caen in France. At CERN, we have developed a program to develop instead a helium-ion accelerator. Helium can be a kind of a best compromise between proton and carbon at an affordable cost. And this is the design of a small triangular synchrotron, 11 meters, for production of acceleration of helium to therapy energies. And then there is another avenue that is very promising, it is being explored, is using high-energy electrons combined with the flash effect. The flash effect is a kind of a recent discovery that shows that in some cases, ultra-high dose rates, if you give a very high dose in a very short time, this has a strong impact on the cancerous cells, but the radiation is not absorbed by the healthy cell. Will be another way, I mean, to reduce the dose to healthy cells during cancer treatment. And then, last but not least, another application in medicine is the use of radioisotopes. There is a lot of interest and excitation about pure radioisotopes that are connected to by radiochemistry. It's nuclear chemistry actually, to targeting vectors, and then can deposit the radioactive emitters really on the cancer. So this is a good way. For example, if you use alpha emitters, alpha particles are very dangerous because they are really lethal to cells, but they act only on a very short distance. So if you can place an alpha emitter on the cancer or close to the cancer, then you can really kill the cancer with minimum effect on the other particles. So there is a lot of interest in new radioisotopes for, in particular, targeted alpha therapy with alphas. So many perspectives in future for nuclear medicine and application of accelerators to medicine. Industry is also interesting. There is a big interest in using more and more accelerators in industry. For example, these are electron accelerators where you mainly use the chemical effect, the chemical impact of electron beams on the molecules. In particular, cross-linking of polymers. You can reinforce polymers with electron beams, and it is widely used in industry. So you can make films and tiles, for example, that are more resistant, thanks to a treatment with an electron beam. It's really amazing. You can weld very easily metals using an electron beam. It is very precise. If you want high precision in a welding, then you use electron beams. When we build our accelerators at CERN, we use many times electron beam welding. It is the most precise way of welding metals. Then there are other applications, like, for example, food sterilization. Nowadays, between 20 and 30% of all the food harvested is lost because of rotting and insects. Usually, now crops are chemically treated. Pesticides that remain in the environment can enter into the food chain. If instead you treat the crops with a particle beam, you can define the energy in such a way that you don't go to the DNA, but you limit yourself, you deposit your energy only on the surface, and you can sterilize the crops without acting on the DNA. So it's a great way of sterilizing crops, but the limitation is the social acceptance of radiation technologies. This is easier in the US, but in Europe, we have many limitations. And really, the problem is that as soon as the public, the people know that there is anything related with radiation and food, this is a kind of a stop. So, and actually, the problem is not so much to extend the technologies, but really to make nuclear or nuclear-related technologies more accepted to the general public. It is improving. Young generations are much more open than old generations, but it's taking time. But I want to tell you about another place where we find accelerators, or we can use accelerators is for the environment. We're saying that particular electron beams have the property of breaking large molecules, and in particular polluting molecules. So you can treat fumes, exhausts with electron beams, and you can break polluting molecules, like, for example, high-order oxides of sulfur and of nitrogen if you use diesel engines. This is also many applications. The economics of this is still to be, let's say, optimized, because we said at the beginning that the energy of the beam is not very high, so you cannot treat very large amounts of fumes. But for example, we made, here in the slide, you see one of the most interesting experience in my accelerator life, my accelerator career. That was when we tested a system to treat diesel smoke from diesel engines. You know, a diesel produces sulfur if the diesel fuel is not cleaned, and of course nitrogen. And this nitrogen and sulfur oxide, in particular for maritime traffic, are very harmful for the environment. So at the time, we have developed a system that where you pass the the smoke from the diesel engine through a circular particle accelerator, and then you cleaned with a jet of water the broken down polluting molecules. We tested this in the shipyard of Riga in Latvia on an old Soviet-built tugboat. It was the most polluting, let's say, ship that we could find to test our system. And actually, it's difficult to see here, but we took a pipe out of the funnel of this tugboat on shore to this that is a movable electron accelerator for treatment of crops for agriculture. And they just gave it to us just before the harvesting season. So we had a time limit to finish the experiment before the harvesting season to try to clean the diesel. And it was very successful. It worked well with nitrogen. We could not test it with sulfur because sulfur was not allowed import. But you see, there are many types of applications in this type that combine electron beams with a chemical effect, and that can be used for the environment. For example, wastewater treatment, sewage treatment, and flue gas treatment from coal power plants. I go to another application, ion beam analysis. With particle accelerators, you can analyze the surfaces of objects. This can have industrial applications. So you send a proton beam onto a surface, and then you analyze what comes out. In particular, X-rays, pixie analysis is very interesting and can be used for analysis of artwork, cultural heritage. And here you have a nice example of a portrait that is analyzed by using a proton beam coming from an accelerator. And this can reveal not only, of course, if it is a fake of a real, because the composition of the paint changes over time. Okay, mainly it is used to show the different stages of restoration, the history of restoration of a painting, and how you can instead use this data to prepare for a restoration. Or you can test different types of artifacts, and I can announce that since a few months at CERN, in our new exhibition area, which is the Science Gateway here at CERN, there is installed a small proton accelerator, 1 meter long, that is the copy of one that CERN has built for the Italian Restoration Institute in Florence. Now, the big one, the real one is in Florence, that is being commissioned for analysis of artwork, but at CERN, we have a copy, another one that is working, and is working in the exhibition area, so the public, the visitors, can see it during operation. And so we had a hard time. So you can do it because the energy to MeV is below the threshold for radiation production. So there are no radiation concerns. So we had a hard time to convince our radiation protection people that there is no hazard. But at the end, they were convinced. And so now, I mean, these type of experiments are done in front of the public, and everybody can see this radio frequency quadrupole accelerator, which is only one of an example of, now I go to my last slides, what are the challenges? I mean, we have seen how many opportunities we have with particle accelerators. What are the challenges? One is cost and power efficiency, as we have seen, and the other is the effect of size. So there is a lot of work now in the accelerator community to reduce the dimension of accelerators. We want really to build a miniature accelerator. There are different ways. There are incremental technologies improving what we have. There are disruptive ideas about using lasers, for example, to power our accelerators. Here you see an example of a 3D printed radio frequency quadrupole. Was the first prototype of a 3D printed accelerator in full copper. Now, this was just a prototype, but the next step, we want to build a real one, and in a few years from now, to produce beam with the first 3D printed proton accelerator for industrial applications. And of course, we hope a lot from artificial intelligence and machine learning. Our machines are also difficult to run, requires a lot of personnel for operation, and if you can automatize as much as possible the design, but the operation of the accelerator, then you can really increase the penetration of accelerators outside of scientific laboratories. Penetration that will take time. Another problem is that accelerators are expensive, and the development of accelerators takes many years. If you want to develop software, it's relatively easy. You just don't need little money. You need little money, and you have the results in a few months or years. You see few examples taken from what I've shown you before. Ion implantation took 22 years, from the first idea to the first commercial application. Medical Linux, the one that I've shown you, the standing wave structure, 15 years. That was quite good. But proton beam therapy, for example, took 38 years to go to the first idea, from the first idea to the first commercial company joining the field in 1995. And only now, as I was showing you, we have the first commercial company producing carbon beam machines, 67 years. So why this? Because it's expensive, because in particular in the medical field is very conservative. So before really going to use an accelerator, you have to go through many clinical trials, and the time to development is very long, but also because the problem is how to transit from scientific laboratories where the new ideas are born and grow, to the commercial companies that then have to bring this to the market. And this is the challenge for funding agencies and for us working in scientific laboratories, how to improve this technology transfer in the future. And this brings me to my last slide. To conclude, I hope that I was able to convince you that accelerators have a big place in the future, and in particular a big place in the fourth industrial revolution. Industry, or our society, is not progressing linearly. All technology always goes in steps. And now we are in the fourth step, that is artificial intelligence, big data, robotics, but mainly the convergence of digital, artificial intelligence, biological, and physical innovations. And accelerators that are only instrument to access the atomic and subatomic world can be essential instruments for physical innovation that already communicate with biology, communicate with artificial intelligence, and have the potential to become crucial actors of the fourth industrial revolution. And on this, I thank you for your attention, and I show again the landscape of particle accelerators. Thank you.
Thank you very much for this very comprehensible and very broad overview. And I hope that everyone is convinced how important now particles are for our society, so every aspect. So thank you very much. So for opening now, so we have, I think all of us, we have a lot of questions that we would like to raise. So maybe I will start, if it's okay, Alan, maybe just because I think I like the question that was raised so in the chat, which was so from in the Q&A, maybe question first. So about the quantum imaging and detection. So those fields are emerging. So for the cancer care. So do you know the leading groups in this area, or how can so the audience here find more information? Leading groups, AI.
Yes, no, this is so sorry, I don't know, because in particular, I think the question is about medical applications, right? Yes, yes. So I'm not expert enough in this. I can find out, but not really on the spot. I can try to answer, but at another moment. And now at the moment, I don't know. I cannot mention a group.
Special group, but indeed for imaging, the keyword, and I think on the web we can already find a lot. I know that there is a lot for detectors, for instance,
yes,
detectors, imaging, so they are, quite a lot of
yes,
books.
yes, because actually the message that I wanted to pass is that the more precise the tool, the scalpel, the more precise the imaging must be. So the two things have to go together. We need a better imaging.
Exactly. And maybe, Andrea, is there any of those team that you would know, if I can? They're asking for the case of the Sesame. So you are muted, Andrea. Maybe not on the top of your head, huh?
Sorry. Yeah. Uh, what would be interesting to know is what do you think, Maurizio, is how far away are we from the production of efficient and beams of singular radiation from small accelerators? So this is something like Eupraxia
Yes,
model of
yes,
proceeding, because that would be very important for the many places in the world which do not accept this technology in this moment.
yes. So you speak about tabletop free electron lasers.
Yep,
So, which is about
exactly.
the idea. Yes, 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 yes. We are not far, I believe, but the problem is that technology still may be too critical to be used on a large scale. So eupraxia is a nice move in the good direction, but eupraxia has two options. One option is using X-band technology from Click, that is 12 gigahertz. 12 gigahertz is it's not easy, I mean, to adjust. It's very, let's say, in terms of stability, is something that is still far from being usable in an industrial environment, for example. And in the same way, also, plasma wake field technology is also very critical. So my answer is I think we are not far from having being able to build a tabletop free electron laser, but we are quite far from the moment when we can replicate this in many units for small universities and laboratory centers, or maybe industry one day.
Thank you. Thank you.
Prototype not far still. So this is good. So maybe, so Alan, I think as well for the good example that was given as well by how Los Alamos has been as well an actor in all of that. So I don't know if it's your question, but then that would be also really nice to hear more. So
Well,
your opinion?
yes, your listeners, which have grown to 135, might be interested to know that the LINAC, the proton LINAC at Los Alamos is still running, and we count the birthday as 1965. So we actually just celebrated the 60th anniversary of the Lance Accelerator. So it's remarkable how much baling wire and chewing gum is being used to hold that machine together
Yes.
successfully.
Yes, maybe let me make a comment, in fact, an additional compliment, that the real feature of that machine was the stability. I mean, how robust and solid the design was done. And the fact that it is still running is a demonstration. In fact. And this is the reason why it went to medicine, where this was the main feature, I mean, the stability. And this was the main invention, to invent something which is stable. And we need more inventions of this type. I mean, not things that work only one day, I mean, and then it break out, but can be very stable for many, many decades.
Yes, when I was directing the neutron scattering center there, we discovered that the time base wasn't accurate enough for some of the experiments that we were trying to do in time of flight. And so the time base was actually based, believe it or not, on the 60 hertz electrical service that we were getting, for the accelerator, which was completely inadequate. So yeah, the accuracy and stability is very important. Actually, my question is short. In short, why carbon? I know that in the early days of the Los Alamos accelerator, we were exploring all kinds of mesons for therapies, pions, kaons, I don't know what all. And that was dropped eventually, but I hadn't heard about the therapies with carbon. Why choose carbon?
Actually, carbon was chosen by your colleagues in Berkeley. So there
I
was on
see.
the Beavatron in Berkeley that they tested different types of ions, and then they came out choosing carbon for the clinical trials because it was a kind of a best compromise between effectiveness, because while proton and X-rays, they act at a chemical level, carbon breaks the DNA completely. You have a lot of double strand breakings of DNA, so it kills the cells in a different way, more effective. And it's the lightest particle where you start to have this effect. On the other hand, it's also historical because then the Japanese continue when the Berkeley closed this activity, the Japanese picked it up and they continued only with carbon. But now, for example, nowadays, okay, we at CERN, we want to go lower to helium, but in other laboratories, they want to go higher to oxygen. So now a lot of people is questioning why carbon, and in fact, probably we will go to something different, but we are exploring both directions.
Very cool. Thank you.
So indeed, all the different capacity, and we heard also with this boron neutron capture treatment as well. So that was like so many possibilities. So the carbon, the helium, and you spoke also, and we would like, so there is a question from Roger Jones as well. So asking if you can appraise as well with the development on the DELF at CERN, so driven X-band collaboration on the very high electron energy machine. So electron energy machine, the flash, maybe if you can expand a bit more. And for example, how many beam lines? So is it 2 or 3? So what are the different energy? He's guessing like 150 MeV that is currently envisaged.
Yes, so I can confirm it's 100 or 150 MeV. Yes, this is the energy. Beam lines, I don't know precisely. So I've seen one beam line. I don't know if they are considering a second one. Yes, and it's one of the different efforts that are, so in Europe, we have at the moment 3 initiatives towards flash therapy with very high energy electrons, moving on different frequencies. So you can choose 12, 6, or 3 gigahertz. CERN is developing this system at 12 gigahertz, and okay, so we are eager to see the first prototype built.
That's really nice. So on the question and answer, so if we go back there, so we have a question from Daniel Santo de Oliveira, who is asking as well if there are any partnerships, so we CERN together with other laboratory for studying, so on particle accelerator, I guess applied as well to medical applications.
Yes, probably yes, apply to medical applications. Yes, of course. So there is the study that I am leading at CERN that is called Next Ion Medical Machine Study, that aims at developing new designs for accelerators for ion therapy, so heavier than protons. So we don't want to be involved in proton therapy because this is commercial. We don't want and we cannot compete with commercial companies. So we try to explore fields where there are no commercial companies. So helium therapy is one. Another is DEFT that we just mentioned, this flash therapy. And then a third, there is also some implication of CERN in Stella. That was another project that was presented in one of your seminars, Christine, and that is building an electron therapy LINAC, robust for developing countries.
And indeed, for the case of the Stella project that was presented by Manji Sodarshan, I think it was really good as well to see how adaptable as well it could be for low and medium income countries. And also thanks to the use of AI, so how it could facilitate and bring as well more robust capacity as well. And indeed, environment is always the important part. So stability.
Yes, I also forgot we also have a small program for design of a LINAC for production of astatine. That is one of the most interesting radioisotopes for targeted alpha therapy. Astatine 211.
Yeah, very good. And indeed, you mentioned as well this small accelerator as well that now we can witness as well in the CERN Gateway. And I put as well in the link, so the paper that you were also presenting with a lot of And so we invite everyone to go there and to understand better how you can make as well measurement. And that could be new topic as well for potential PhD that could come there. So more questions also from anonymous. So, but we so there is wondering, so how much as well of this ERTIS. So the ERTIS. So
Yes.
can you explain a bit more now if we look at the environmental aspect and application of this accelerator?
Yes, but HERTIS was a very promising idea. The point is that as soon as we have developed this system to remove pollutants, then the shift moved to carbon, to decarbonization. And then all the money that we could get from, usually these type of applications are funded by programs from the European Commission. And now all the money of the European Commission went to decarbonization. And it took some time for us to include also carbon into our carbon dioxide in our chain chemical reactions that we can excite with electron beam. Now we have a scheme also including decarbonization, and we are now looking for funding to move the experiment on a real seagoing ship. So the point is to bring the accelerator on a ship with all the rolling and instability and the kind of technicians that you find on a ship that are not really what you have in a scientific laboratory, and see how, if we are able to run the accelerator on a ship. But this is the next, let's say, step. But we are still looking for the funding from the European Commission, not funded yet.
Exactly, and there we can also recall this so challenge-based innovation, so that you are also encouraging, so with looking at how particle accelerator for environmental aspects as well could be used, and that can bring novel ideas as well. I think this is the important thing to bring capacity as well by enlightening what particle accelerator can do, and then to identify the different societal challenges, so by the audience there as well. So I think it's really good too. So beyond the current application, so what emerging societal challenge could accelerator technology address in the next decade? So if you can give like the most challenging one, for instance, what would you say?
Well, I think that there is a lot of space, for example, for neutron radiography. So something that I dream of is making a small accelerator to produce accelerating protons or deuterons to produce neutrons that can be used to inspect material, for example, bridges, concrete structures, to see the status of concrete structures. You know that now all our road infrastructure is very old and needs some check. Building portable accelerators to produce, X-rays, but also neutrons that can be used for inspection is, I think, something that has a big future. Yes. And then there are many, in terms of nuclear applications, there are many things that are at the interface, that are that type of, say, nuclear reactions that are induced by accelerators that can have application in society that are not being exploited, because for many years the word nuclear was somehow forbidden. Now somehow the public is more, let's say, is wiser than in the past, and they understand that under strict control this type of technology can be deployed, and this, I think, is something where there is a lot of space, I would say, in the future. Yes.
Yeah, I fully agree and endorse, of course, the first part with the neutron, the compact neutron as well. So looking at the spallation, the big neutrons that we're building, the capacity as well to observe the matter and to try to build with and thanks to those neutrons to understand hydrogen, any kind of DNA or any kind of protein in a better way. That would be really glorious. So this is where we need more scientists. So I like this point. So another question, so by Oza Samuel Olombrua, who is asking as well, looking back for the internship at CERN, so preparing someone to work on accelerator application in industry, so like a healthcare or clean energy. So do you know any connecting with industries and clean energy?
No, it's difficult, and actually, and I take another of my hats. I'm also coordinator of a European project for R&D and accelerators, where we had a program to fund exchanges between laboratories and industry. Really, we didn't have enough applications. So because of IP protection, because people in industry is very busy and they don't have really time even to follow people coming from the laboratory. So seems that the two worlds are really quite apart, and it is difficult to build bridges between the two worlds. Now we are trying, so tomorrow I have the first meeting to prepare a CERN accelerator school on medical accelerators. I give you a pre-announcement, will be in June 26. And one of the topics that we discuss in the program committee is how to involve the industry in the school, how to have lectures from industry, and how to train people who at the same time can work in the labs and in the industry, in particular on medical applications. So it's a challenge, sociological challenge, not really technological, I think.
Technological, maybe to try to see what are the limits as well in the current technology, because that could invite those industries as well to build maybe faster equipment and something for the flash, for instance, especially just to get the state of the art. But indeed, this is what I think, as you said, this is crucial, this connection with the corporate, to try to enhance as well this capacity, maybe for some project that could with experiment, so like what you have, and with the industry that could sponsor, like with the light source, or the with Andrea, so with the sesame, or with the neutron source that we have at ESS. So very important aspect. So maybe the question from Sirius. So I see that you have been hanging your hands.
No worries. So actually, I would love to ask my question later, but point you to 3 people who have raised their hands for the participants, amongst which are good friends, one of which is, for example, our good friend Malik Masa, and Munia is also in there, and they had the hand much longer raised than me.
Okay, so then we wait for you, and we will have, so then Munia, please. So can you speak or ask your question live? I give you the mic.
Yes, sure. Can you hear me right?
Yes.
Yes, perfect. So first, I would like to thank you for organizing this session, and I would like also to thank the speaker for this wonderful overview on particle accelerators for society. So I'm not sure if you are aware, but we are currently actually developing the applicant strategy for fundamental and applied physics, which aims to define the education and also the physics priorities that can have the most significant impact for Africa. And I believe that you are aware that one of noteworthy example of progress in accelerator physics is the ITIMPA labs in South Africa. There are also facilities like CERN in Nigeria and Pilitron in Ghana, contributing to this momentum. So actually, given this growing development of accelerators, accelerator physics on the continent, what key recommendations would you give to African policymakers and scientific communities to effectively develop accelerator infrastructure and the expertise taken into account long-term sustainability and also impactful contribution to both local and also global scientific challenges?
Okay. Thank you for your question, first of all. I think it's a very important question, and it's in the interest of everyone to spread these technologies. And you don't need much. I mean, a small particle accelerator is something that you can build in a university. So we have, I give you an example. So we have now a collaboration with the University of Sarajevo in Bosnia, where they have basically nothing. So it's, and with some funding from a donor, we are buying an ion source. We are setting up a beam transport system that will be, first of all, installed at CERN with some people from Sarajevo working at CERN, and then it will go to the Sarajevo University, where it will be permanently used for ion beam analysis. So ion beam analysis is a perfect entry point into the accelerator technologies because you need only a proton accelerator of a few MeV, so you don't have radiation protection issues. So the problem they have in Sarajevo is that the laboratory is next to a lecture hall. So really they have to be very careful with the accelerator and not to give troubles to all the university. But these are things that don't need much money and much expertise and are relatively easy to do. Or you can start the other way, instead start with a small electron accelerator. And this is maybe even easier to procure an electron ion source and then start with some accelerating structures. So nowadays, I think that it's something that is relatively affordable. It's very good for training students. And then, like we hope, for example, for this Sarajevo test stand, is that we will have our 3D printed accelerator. We would love even to test it there. So then it becomes that they would be really in the big business. So this is what I can, let's say, I can suggest I can to do in this direction.
Thanks a lot. Thank you. Appreciated your answer.
Thanks a lot for the question, Munia. So indeed, we recall so the African strategy, which is many discipline, but indeed this one looking at the accelerator part and the African light source as well, and many aspects so could be very interesting. And then I would like also to mention this IUPAP, International Union of Pure and Applied Physics, and this working group 14, where we have as well, we are gathering all those different world expertise and try to see where the different direction could be. So what could be interesting, Munia, is as well, between this African strategy, between the IUPAP and this APS FIP, we could construct as well some, project or paper at least, where we could gather all those different existing capacity as well. And
Awesome.
see with
Awesome.
the governing body, because exactly as you said, we know that in Africa, that's one of the difficulty. But if we have example and concrete example, for instance, there I would give as well this X-Tex lab, where in Benin, so there is so this capacity for having built for the diffractometry quite a lot of development. So I think it would be really good to mention that. So we'll put this. And I really would like now to indeed to have, so Professor Maza, so can you please, are you still there? Maza Malik, I don't see you anymore, unfortunately. So we will hear him and we can ask him the question next month because he will be our speaker. So it will be really good to hear his view because speaking about experimental applications, I think he can give us more example. So then I read back some of the questions back to the
He is still there. He is still there.
Yeah, but he doesn't have his hand on, so I will.
Oh, okay.
Yeah.
Yeah.
So he's raising their hand back. Okay, so now you can speak. So Malik, you're back online. So give us example, please.
Thank you. Thank you so much.
South Africa.
Yes. Thank you so much for organizing this outstanding talk indeed. And my congratulations for the professor, the speaker, Vretenar, who gave us this comprehensive talk and vision on accelerators. Prof, you have mentioned that the bulk of the energy injected in the accelerator is lost in a form of heat. And how can I say, it's just a percentage which goes really, truly to the accelerator. It seems that the recent advances in lasers, in particular petawatt type lasers, have showed that it might be possible to have a tabletop accelerator whereby the energy input is not high. Do you think that such a kind of accelerator based on lasers at the type of petawatt would be a reality one day? If so, when? By when? Thank you.
By when is a different question. Maybe one day, yes. So actually, to me, I mean, this is a very important development that we have to continue. Petawatt lasers can be a way to go. I don't know how they are in terms of efficiency. So lasers don't have a good reputation in terms of efficiency. Usually they are very inefficient. So the energy that you can achieve is high, but the energy that you take out from the power grid is usually also very high. I have many expectation on terahertz laser acceleration. So this is something where also that you can use dielectrics as media to transport your beam and excite dielectrics with terahertz lasers. This to me is a very promising direction. The point is that if the limitation you have seen already with the conventional accelerators, the limitation you are limited in terms of total energy that comes from a limitation in the number of particles that you have in your beam. When you go to this type of accelerations, you have even less particles. You can have high energies, but you have very low intensities and very low total energies. So again, I see that these technologies have a future. I cannot tell you when, definitely not for the next 10 years, maybe later. And it will be for a different type of accelerators. So they will not replace our standard accelerator technologies. They will complement them for some specific applications where you need high energies and low intensities and small dimensions. For example, some applications in medicine. I don't know if I've answered your question, but I don't have my crystal ball. It is under repair since a few years, it got broken.
Thank you.
Indeed, with but the laser and the wake field, I think it's quite also promising in some way. So back to what also Andrea Lucy was saying.
Yes. But I say I don't discourage our young students who would like to join this field. On the contrary, I encourage them. While I discourage my older colleagues, so this is not for you, it will be for the young people.
So this is for all of us and everyone could and should work on that. So now back to SRF, which I think is also an interesting one. So we know that there might be some limit there. So this is why now with this wake field or plasma acceleration might be faster and more sustainable in that sense. But so the prospect for this SRF technology, so outside of science. So it seems that the next the next generation technology. So what would be the limit for expansion? So from this science today. So indeed, this might be that.
So you're speaking of superconducting radio frequency, SRF.
Exactly.
Yes.
That's
Okay.
right.
Yes. We have seen that there is a large need of high intensity electron accelerators. So you can do a lot with accelerators for ferritons of high intensity, relatively low energy, and this is an ideal playground for superconducting radio frequency structures. Nowadays, there is a lot of work in coatings, superconducting coatings. So in the past, all these structures were just made in bulk niobium. It is expensive and difficult to machine, and that's it. That was it. Now, I mean, you can do wonderful coatings with materials that are not niobium, but niobium alloys, niobium tin, for example. You can do micro layers, you can do multiple coatings, and this, I think, is a very interesting direction that will increase the efficiency of the structures. We have seen already now, I say, you can reach 50% efficiency. Probably you can do more if with, for example, coatings that can operate at high temperature. High temperature superconductors applied to RF. This is something that I believe is very promising, and maybe something will come up before 10 years there.
Indeed, so for the material, because material science is really what will help us for those efficient, so cavity SRF. And then I could maybe also...
Yes, and maybe I can tell you of another dream that I have. The problem is that I dream too much. This is my problem. But another dream that I have is multi-material 3D printing. With 3D printing, you you can imagine of doing multi-materials, layers of different materials, and really build your structure, grow your structure with multiple materials. You have a huge freedom you will have one day to really to go in the direction of increasing efficiency and reducing dimensions and cost. So this is the final goal.
So that's hopefully not only a dream, and we'll manage it. So with some of the new generation and the next generation recall as well for the quantum. So those SRF could be used as well for this qubit. If we go not for the megahertz, but then towards also the gigahertz, there could be as well a lot of capacity for, and we might need to have also one presentation on that, because that's
or terahertz maybe.
Exactly. So then we could look at the safety as well. So how safe is it to use an accelerator? So with an existing crew on board. So in a hospital, for instance.
Well, hospital accelerators are designed to be safe. And actually they have to go through so many tests and quality assurance that they are absolutely safe. Definitely. On scientific accelerators, you have to take some precautions, and also, of course, you have to take some precautions when you design a medical accelerator in design phase. Yes, but an accelerator can be made safe.
And this is why industry have to comply with the authority local. So in this is super safe. In laboratories, as you say, maybe we need to see, but there is always, of course, the training and the people with radiological for sure. And IAEA being also behind a lot of those different treatment development and with radioactive, with nuclear.
But sorry, in particular for a medical accelerator, really licensing is a big fraction of the cost. All the procedures that you have to make it licensed as a medical device. So get a stamp of being allowed to operate as a medical device. This is a large fraction of the cost.
The cost and the time and engineering.
The time and the people.
So this is why it has to be designed to make sure that first we understand what those laws are and how to make it the lead way. So we have one more question also from Linda Connect, so asking as well for the concept of this flash therapy, so which is intriguing. So how does that really work? So maybe you can record us that, and why is it so effective, so on the cancer, and yet does not damage normal tissue, so giving the high dose rate. So it seems indeed so counterintuitive, to say the least. And I really like also this flash therapy. So what will be the future? And what are the limits of this future?
Yes. So first of all, I think that nobody can give you a clear answer how it works. So there are at least, I think, 5 or 6 theories, ideas, why flash works, actually. At the beginning, people were convinced, and I also was convinced, that it had to do with the oxygen depletion. So with the metabolism of oxygen in the cells, that doesn't have the time to develop. Actually, there must be somewhere a time constant, something that there is a time threshold somewhere, a time constant, something that doesn't have time to develop in order to make the healthy cells aggressed by the radiation. But exactly what is the mechanism is still under study, and there is not yet a clear answer. So about the oxygen, some experiments recently seems to discard this hypothesis. But I still think that maybe then some other experiments will come that will confirm. Who knows? But it's still a mystery, in a sense.
And if I remember at the EPFL, isn't it in Geneva, I mean, or close to in Switzerland, they were doing some different measurement there and tests.
Yes, in the Lausanne Hospital, CHUV, CHUV Hospital in Switzerland, because actually this was discovered in Paris by the Institut Curie, the flash effect, and then the Lausanne Hospital joined and made now it's one of the leading research centers for research on flash. Yes, but now we are waiting for the first large-scale application of flash because of the lack of accelerators with high enough energy all the experiments were only done on, let's say, on the skin or on very really at the not penetrating inside the body, but at the surface. So we want to see what happens if you really start to do experiments inside the cells and inside the animals first.
So I think it's really an interesting call for companies also or corporate that are listening to us. So I think it's
Yes.
topic to develop. So another question, so Giovanni Tugliani, so is asking as well for so how is it possible to feed the RF cavity with laser? Is it possible? And what
No,
are their studies?
Sorry, it's no longer an RF cavity. So lasers you can use either to excite a plasma, and then the medium where the electric field is developed is a plasma, is no longer an RF cavity, okay, fed by the laser. Or instead, you can feed with a laser a kind of a structure made of dielectric bars. It's like a room with columns of dielectric. You send a laser, and the laser will generate the transversal accelerating field. And always the problem is that in the laser, the electric field is transverse to direction of propagation. And you always need to have a kind of a 90 degrees between the laser and the particles. So you have to deflect the electric field in the direction that you want. But it's no longer a cavity.
It's another technology, but still a lot of study there with laser to make them indeed effective. So question in general, also from Orasa Owana, who is asking as well, being an undergraduate student, so in Physics Matters, so do you know any leads to exchange programs, scholarship, such as international student? So maybe we can refer to what you mentioned before, but undergraduate student.
Yes, no, I don't know if it's a student association in this field. No, we have to make one probably.
Yeah, to check this out. And that's also a good question, I think, for Munia. So looking at on the African continent, how to start up potentially syllabus and such type of development. So from Dimitrios Christos Savini, so he's asking as well, so how much far away so are we from an on-chip acceleration for radiotherapy application?
On-chip, okay. This on-chip is another way to call these dielectric laser accelerators that I was mentioning before. This of sending the laser into this dielectric structure and creating this electric field. So for medical application, there is a problem because on the one hand, it is true that you don't need intensity. So, and I think that we are not too far from having an accelerator on a chip to produce a very small beam, yes, in terms of intensity. The problem is that the medical application is where you need the highest stability, and you have to know very precisely your beam, and we are very far from that. So my opinion, that is my humble opinion, is that we are not maybe very far from having a beam out of a chip, but we will be very far until the doctors will accept it on a medical device. The doctors and the licensing authorities will accept it, might accept it on a medical device.
Indeed, so there is some thought to try to make it reliable. So in that sense.
Yes.
So radioactivity, yeah.
Yes.
But that was a good question. So is it possible to use a ring accelerator, so in quantum computer? So I don't know if you know the answer, but because of the high bunch of ion, the ring.
No, I have no idea.
But I think we might keep the question for Philippe Chomaz, who presented last month as well. So this quantum computer, or we can ask the question to the community. So Linda is indeed so happy with your answer, speaking about the flash and then the experimental results. So we will look at the future. This is true, Linda. The future will tell us everything. And then we have for Sumba Tiwara. So how can we overcome the problem of cost and availability on radiation therapy at ground level for the general public? what are the advice maybe, or do you know some kind of way to limit shielding, of course, but
sorry, you speak of radiation therapy, which is conventional radiation therapy with X-rays, or what type of therapy? Yes.
Radiation therapy, so that would be X-rays.
So radiation therapy with X-rays, yes, there the main limitation is the cost and reliability of accelerators in difficult environments. So what now limits the diffusion of radiation therapy in developing countries is the fact that it is difficult to get all the structure with spare parts, maintenance, and to have the infrastructure that you need around the machine. So often in some countries you have modern machines that are still in the box because they don't have all the infrastructure that is needed to make it run in a reliable environment. And there is the project Stella that aims at making the systems more robust and easy to operate for developing countries. So there the limitation is to the penetration, let's say, is mainly the environment. While for particle therapy, the limitation is the cost, basically. So the fact that the cost per treatment is higher, and so the quality of life, that is the main advantage of particle therapy, has a cost that is still not affordable for some countries, for some public health systems.
Exactly, and the reliability and the operation as well, because you need a lot of operator to be able to handle.
Yes. And okay, maybe you don't, but at least this is now the business model, is that they sell you the machines with the operators, with the operation contract. The machine is still operated by the company for many years, and you pay a yearly fee that is quite important for operation. And this is why I think that we hope that artificial intelligence and machine learning will come, to change the business model, so that not really, you can buy the machine and then a nurse will be able to go there, push the button and just run it without the need for expensive operators. So this would be a big step, not only in terms of cost and also of accessibility of the systems.
Yeah, and there, indeed, I would recall again from the Stella project what was presented by Manji, and as well maybe the caffeine, all the work ongoing at CERN, which was developed by Luigi Serio. So how to make it more effective, indeed. So good point. I would like just to mention as well, so indeed, Alan noticed that for the question of the carbon, so why carbon? So the question as for low carbon Bragg peak is at the maximum of the biological efficientness. So this RBE, so versus the linear energy transfer, LEUT. So this is also one of the apparently reasons, so that was given so by Marco Piglia, and you agree with that. We had indeed more questions in general for all the different programs. So I think we will mainly put some reference to what you mentioned, so at CERN and in Africa and elsewhere. And then looking maybe, so for the hadron therapy, which type of accelerator is best, a cyclotron, a LINAC, or a synchrotron? That's an easy one.
Okay. It's a matter of religion, basically. So everyone has his own religion, and you don't, the one that you learned when you were a child, and it is difficult, to say who is the best. So my religion is synchrotrons and LINACs, and so of course I believe that synchrotron and LINACs are the best. My colleagues of cyclotrons will tell you the contrary.
Depending where you are, indeed, if you have a cyclotron, I think it's really good, but especially for the radioisotope as well.
Yes,
and that depends.
Yes, but let's say that in general terms, the higher you go in energy, the more justified is the synchrotron. The synchrotron is accelerator for high energy, the cyclotron is accelerator for low energy. And in between, there is this intermediate region where there are different opinions. Okay, and unfortunately, the region that you need for ion therapy is the one in between, where you have either you stretch your synchrotrons to start from low energies, or you stretch your cyclotron to go to high energy. And actually, the answer may be this: none is the best. That maybe we still to invent something which is better than any of them.
So we need everything indeed, and it depends on the economy as well. So it's not simple to build a synchrotron.
Yes, yes,
So
yes, yes. So anyhow, so we will still stay with many religions, actually. So there is no way, I mean, to go to a single religion because every type of accelerator, every type of machine has its own, let's say, niche where it is really the most effective.
but still a lot of R&D there that will be welcome for the health being improved as well in the future. Some compact accelerator are the key, so as you mentioned, so it's really good. So thanks a lot. So I think that we'll need to give the channel back. So we have reached like more than 1.5 hours. So many questions. So thank you everyone to have raised and participated. So a lot of thanks from everyone. So to you, so Maurizio, thank you very much for this very pleasant moment that we spent with you. So we will provide more information. So the slide will be available. So next week we'll have as well the recording on the website that shared. And we can connect and contact in the everyday's life. So the different people who has been as well in this panelist for more questions. And I just want to finish by sharing my screen and having a possibility for introducing next month. We'll have in March, 27th of March. Be careful, there is a time change which between continents will not be in line, but aligned. So at 11 in US, but then at 4 p.m. in Europe and in most of Africa. And that's going to be maybe a bit more technical, but we'll have the pleasure to go back to this quantum trapping, so of a cold neutron, so with picosecond precision. And that's going to be, so Professor Malik Maza, who will present this exciting topic. Recall that we are in this International Year of Quantum, so that will give us possibility to hear more and to know more about this wonderful and exciting time. So we can then, I think now, so thanks again, so Maurizio Vretenar, for all those precious information. We've learned a lot more about Los Alamos as well. So thank you, Alan, for enlightening us for those 60 years. We have a lot of anniversary and tomorrow as well. So happy birthday to Erwin Schopper, so 101 years old. To Maurizio, 40 years at CERN, and to each of us, one more day in life, in good health, thanks to Particle Accelerator. So thank you, everyone. So we'll stay tuned, and then we'll meet soon. So on this channel. Thank you, everyone.
Thank you.
Bye.
Thank you.
Bye-bye.
Bye-bye.
Thank you, Maurizio.
Bye.